All right, so in this video, we're going to take a look at this predator-prey situation, right? We mentioned it a little bit before in the last section, this idea that these differential equations can represent competing populations of things, and we can kind of figure out what happens long-term or at specific points based on using usually Euler's method to be able to approximate some solutions here. So let's take a look at this investigation. It says when a population X of size X, right? So like the name of the population is X, and it has a size of some specific value of X, increase at a steady rate, and that we'll call that rate alpha, proportional to the size of the population. We can write the differential equation describing their rate of growth as dx dt equals ax, where this equation would lead us to some kind of exponential growth, which would allow us to understand that x is going to equal capital A e to the at. Right? There's going to be some kind of exponential growth that's going on here in terms of a's, and like basically we can take this differential equation and turn it into this exponential growth, right? And we'll kind of get to, we kind of got to build up to why this matters in a minute. So now it says, suppose there's this species y, has a population size of lowercase y, and it's in competition with x. The rate of increase of x is now affected by the size of y, right? Like if they're competing for things, x depends on y, and it does so in a way such that y increases the rate of increase of x will diminish. So as y increases the rate of increase, so like basically as the rate of y goes up, x will go down, right? So the simplest way to do this would be to say, okay, well, dx is this a minus by times x, right? So this kind of represents the population growth of x. And this symbol, right, this is the rate of x, right, of the population of x. And that thing in brackets is kind of like the growth factor, is the way to think about it. And so it says here, as the population of y increases, the rate of growth of x decreases. If y is competing with x for the same resource, then the equation for the growth of y it has a similar structure, just different, right? So like if I want to find the growth of y, so this is the rate of y, like the population, the rate of change of that. It depends on this, represents kind of the population of y growth, if you want to think about it that way, times some value of y, right? So one of them is, like this one is a value of x that's affected by some amount of change of y, and this is a value of y that's affected by some amount of change of x. And so if for example, though, species y is a predator and species x is a prey, then the equation could be this way, right, where x is decreasing based on y, and it might be more appropriate to put it that way. So all of this kind of like growth and changing to say, like, let's get to kind of the actual idea of these. So it says, let's explain why this equation might be more appropriate than the previous one for a predator-prey situation. And the reason to really think about it is y wants to eat x, right? Like it's the predator. So more of species x is better for y, right? Like the more you have of x, the better for y, because they have more things to prey upon. And the second of those equations shows that shows that if you have this positive value of x, then it's better. It's a better representation of what is actually happening. And so these types of equations are often referred to as the Lacca-Volterra equations, sometimes shortened to LV. But everything we've kind of done up here in discussing these isn't super important because you'll never really have to build the equations on your own. You'll be given the equations. And so it's just our attempt to try to understand where these equations come from. So down here in this next part, we're going to actually look at an example and figure out, okay, well, how are these connected? So in this part, it says the population in thousands of fish and of sharks in hundreds, right? So notice that X is in thousands and Y is in hundreds, and time T is years, is given by the following equation, right? So the change in X, so this represents the change in amount of fish, is given by this equation. This one is the change in amount of sharks, is given by this equation. So notice they gave you the equations, right? The part above was just attempting to try to understand how these equations come to be, but really you're not going to have to because you just need to know what the equations are. But notice these are not linear. You certainly could not solve this system of equations directly. You couldn't even do a phase portrait for it in what we've learned so far. So the only way we're going to be able to do this is by using approximate solutions. We're certainly going to have to use Euler's method to kind of come up with a best guess as to the solution to this. So an important kind of term is these equilibrium positions. So equilibrium positions are pairs of values x and y, such that the change in x is 0 and the change in y is 0, right? They basically, since it's equilibrium, they're these stable points in population, right? It's basically if the change in x and y are 0, then the populations aren't changing at all. They've kind of hit this balance. They've hit these equilibrium positions. And so here it says, well, let's find 2 equilibrium positions of the populations of fish and shark. So let's take our first equation and set it equal to 0, and our second equation and set it equal to 0. Right? So we want to figure out when the change in fish and when the change in sharks both equal 0. And so we'll take a look at the one on the right first. So I could add 2y, so 2y equals x over y. I could divide by y. If I divide both sides by y, I get x equals 2. So in this case, x equals 2. And then I can use that to substitute over here. So 3 times 2 minus 3 times 2 times y. So 0 equals 6 minus 6y. 6y is 6, so y is 1. But we have to remember the units, right? So x was in thousands, so 2,000 sharks. And y is in hundreds, and 100, or sorry, y was, I have to switch, 2,000 fish. X was fish, and y was sharks in hundreds. Right, so what this says is if you get to a population of 2,000 fish and 100 sharks, the populations will not change. They both have a rate of change of 0. It's this equilibrium point. Okay, so then for this next part, we're given some initial conditions. Here are our initial conditions. Okay, it says initially there are 3,000 fish and there are 2,000 sharks. So to write this in terms of x's and y's, right? X is actually 3 because it's fish are in 3,000. Y is actually 20, so that's 0.2, right? Because sharks are in hundreds, so it's 0.2 hundred sharks. Basically divide that by 100, right? Divide by 100, divide that by 1,000, you get your values. And that happens when t equals 0, right? When time is 0, you get 3 and 0.2 as your x and y. So then it says, okay, well, let's use Euler's method with a step size of 0.02 years to show that when t equals 0.02, there are approximately this many. Right, so these are the answers we should get. Let's figure out how to actually do it. So we have to set up our 3 sequences, just like we did when we were looking at our approximate solutions. So my first sequence U1 is going to be, for me, it's going to be fish. And I'm going to say, okay, well, xn plus 1 is going to be xn plus my step size, this, 0.02, times my derivative, my x derivative, basically, right? dx dt, this. So that is going to be 3 times xn plus 3 times xn times yn, right? 3x plus 3xy. That's what this equation is up there, right? 3x plus, or sorry, minus. There should be a minus between those. Minus 3xy. So minus 3xy. So then I have to set up my second one, which is going to be sharks. And that's going to be yn plus 1 is yn plus 0.02 times my y derivative, which is xn times yn minus 2yn, right? Because it's x times y minus 2y, which is what I have written there. And then my third one is going to be time, and that is always just tn plus my step size, 0.02. Right, and so then this is where I need to go to my sequence app and go type in my stuff. So we can do that quickly. My first sequence is xn plus 0.02. So I'm just going to modify what's in here, 0.02 times 3x. So that one's right. Minus 3. That needs to be a 3. Times u times x times y. Right, so my first one is correct. It's n plus k. I start at 0, but I need to change my initial condition. The initial condition for x was 3. So now I need to go do my y sequence. So that is u2 plus 0.02. I need to change my step, 0.02. 0.02 times x1, which is that one, times y, so u2 of n, minus 2 times u2 of n, so that one was actually fine. And I'm in n plus k, I start at 0, but my initial condition when time is 0, the y value was 0.2. And then my final one is that equation is correct, right? u3 is t, so t of n plus 0.1. I start at 0, it's n plus k, and t starts at 0. So then I want to go look at the table. And it tells me, if I look at what it asks for, it says show that when t equals 0.2, there are approximately this and this. So when t equals 0.02, then in the table, x equals something and y equals something. So in this case, x, when this is 0.02, oh, I see my mistake. My last equation was not correct because I didn't make the step size right, 0.02. Now it has my correct step size, right? So there's when that u3 is t, so when t is 0.02, I have 3.144, and y is 0.204. 0.204. But remember, to find my fish, I need to multiply by 1,000, and my sharks, I need to multiply by 100. So that times 1,000 is 3,144 fish, and that times 100 is 20.4 sharks. Right, so I've shown that I got the same answers that they said we should. Okay, so now it says from your table of data, write down the maximum number of fish and the corresponding number of sharks. So I'm going to go look at my table and find that out. I'm going to look for the first time the fish maximize. Right, so basically like they're going to rise to a point, they're going to hit a maximum, and then they're going to start to fall. And then they might start to rise again, but I'm just looking for the first one. So as I start at 0, I see they are rising, right? 4.5, 4.9, we're in the 5s, we're in the 6s, 7s, but then I start to go back down to 6. So somewhere in the 7s it goes down, up, down, right? So that was the maximum, and that happens at time 0.52. So at times 0.52, so 0.52 years, x equals 7.477 and some decimals, 477 and some more decimals, and y was 1.025 and some decimals. Right, but remember, to get this, it's times 1,000, and this is times 100. So there are 7,470, I gotta look at what that rounds to, 78 fish. There are 103 sharks, and that happens after 0.52 years. Right, so after that amount of time, we reach kind of this first maximum. And so then the question is the number of sharks at this point what you would have expected from the differential equations? That's really just an opinion. And you'd say probably it's what I expected. When we looked at the initial value was 3,020. After a very small amount of time, fish went up and sharks also went up. Right, they went from 3,000 to end up from 20 to 20.4. So we would kind of expect after a certain amount of time they'd continue to go up, but eventually would probably die out. Maybe not enough space or whatever it is. So let's take a look at question 5. So question 5 says, let's plot the values of x and y on a set of axes from 0 to 3. Right, so this represents the first 3 years of these populations, plotting every 0.2 years, and then we can sketch, we might not sketch it, but we can talk about what the trajectory is. So to do part A, we can copy the data from the sequence app and paste into stats2 variable. Right, because I have an x and a y, I'm going to look at stats2 variable. And so what we can do is we can take the first 3 years of data. We just want the x's and y's, right? And so you can, from here you can do a selection, and I can move the boxes so that I get the first 3 years. Right, this will take a little bit of time, right? That's 1 year. I've hit almost 2 years, and then I need to get to my 3rd year. Right, almost there, 3 years, right? So I have x and y for those 3 sets of years, so I can go copy, and I've copied that selection, and then I'm gonna go to stats2 variable to dump it in there so I can see a graph. Let's get rid of what's in there, and let's paste all of this, and we're gonna do it as grid data, right? And so it's done it, right? It's taken my first value, x and y, and I've done it all the way for 2 years. And so we can take a look at this, right? We can plot this. I can kind of see what's happening, right? The data over time is x and y are increasing to a certain point, but then x starts to decrease and y continues to increase. And then at a certain point, both x and y are decreasing, right? So this is just showing a visual representation of what's happening over time. And so, and so we can kind of look at this data, and we'll come back to this graph in a minute. We don't necessarily need to sketch it. You won't really be asked to sketch it in an exam. But it says, what does this suggest about the non-zero equilibrium point? So that non-zero equilibrium point that we found before was 2, 1, right? I think, let's double check. Yeah, right, when x was 2, y was 1, right? 2,000 fish, 100 sharks, right? So it was 2,000 fish and 100 sharks, not 1,000, 100 sharks. Basically, let's look at where that is on our graph. So if I start to look at some of these points, right, I see that I'm certainly reaching x values of 4, but if I go backwards, I start there and I'm at 3, 0.2. And if I go over here, I'm at 1.7, right? So the 2 happens somewhere over here. But when I get to these values that are close to 2, y is way too high, right? So I don't actually hit that point of 2, 1, right? 2, 1 is a point in, I can't draw it on here, right? But it's in the middle. If you look for the point right 2 up 1, it's not one of my data points, right? So what that means is the equilibrium is not reached in the first 3 years, right? So this spiral, if I was to continue to go, it might continue to kind of spiral inwards, if we want to think about it that way, right? Like the graph looked a little bit like this. It started here and started to do this and then came down here. It might start to go in and it might go here. And then eventually it might hit a point of 2, 1. But it doesn't do that in the first 3 years. Right, and then just a note that we kind of skipped over for a second. It says to sketch a phase portrait, we could copy the required section. It tells you how to do it. And then we can put it in stats2 variable. So basically what we just looked at was a phase portrait, right? What's happening over time. This is the calculator kind of sketching a phase portrait for us. But again, it's an approximation because we used Euler's method to get those values. So then part 5 says, well, explain from a consideration of the actual differential equations why the population of sharks continues to grow once the population of fish has started to fall. Right, so population of fish start to fall over here, right? Both x and y are increasing right here, right, as I'm going from left to right to here, until I get to this point. Y is still increasing, but now x is going back down, right? And so we're saying, well, why does that happen? Why does y continue to increase as x gets smaller there? And so if we look at our equations, right, dy dt was xy minus 2y, and dx dt is 3x minus 3xy. So for sharks to decrease in population, then dy dt needs to be less than 0, right? Like you have to have a negative change in y. So then that would lead to xy minus 2y must be less than 0. So xy must be less than 2y, which means x must be less than 2 if I divide by y, right? And so this kind of says, we can talk about it in here, if the population of fish is less than, remember that's 2,000, the sharks decrease, right? If the population of fish is greater than 2,000, sharks will increase. Right, and so here we're saying, well, sharks are still increasing because the population of fish over here are bigger than 2,000 until we get to this point 2, right? Like 2 is approximately here, and at that point, sharks start to go down again. So as long as there are 2,000 fish, right? As long as there are at least 2,000 fish, sharks will continue to increase. But once they drop below 2,000, right, sharks maybe die off. There aren't enough fish for them to eat, right? So they start to go down. So this kind of 2,000 is an important part for the fish. So this last part says, let's sketch the graphs of x and y on the same axis with t on the horizontal axis. Here it says you need to set the axis n needs to go up to about 500. As does x. This is just giving you a note. You're, again, not really going to be asked to do these, but let's take a look at it. So if this is time on here, and these are our populations, right? We're saying, okay, well, what's happening is the population of fish, for example, we don't have to be super accurate, right, are doing this. Like they're potentially growing, Actually, yeah, fish started by increasing, right? Fish started by increasing, but then they started to go down, but then eventually they'll come back, and they'll go down, and they'll come back, and they'll go down, right? And then sharks, so that first thing we drew, this is an example of what's happening with fish. Sharks also went up, but then at a certain point, they started to come down. I think they started to come down after, so maybe they went here, right? And then they hit here, and then there's also this, right? So like they're gonna intersect at these certain points. We don't know what those are exactly, right? We're just drawing a general idea. These are the sharks, right? But what we'll notice is these will be equal potentially at some times. They might not be equal at all, right? But it's just showing that these things are not cyclical because they don't follow, it's not like a sine graph. They're not the exact same every time. But it just shows that these populations will be changing, right? Increasing and decreasing at different times, increasing and decreasing based on what the certain values are. At a certain point, it can hit an equilibrium. But again, like we found an equilibrium point was at 2:1, but that doesn't happen in the first 3 years. It takes a while for it to get there. Again, not a super accurate sketch, but you won't be asked to do these sketches, so you don't have to worry too much about it. Right, so this is an idea of taking an actual application, right, a set of differential equations that are not linear, and using those in the context of this predator-prey idea to find something like an equilibrium point, but then also to figure out what's happening long-term, maybe to find a maximum of something or a minimum of something, and then figuring out some long-term information or some information in the future about these populations.